Есть старая известная шутка о том, что какой язык учить, Python или Go, или, возможно, Ruby. Есть правильный ответ — учить надо английский, так как это лингва франца для разработки. Наш следующий спикер будет рассказывать по-английски, сессия вопросов и ответов у нас будет по-английски, так что давайте я тоже попробую переключиться на английский. And our next topic is about thread safety. Actually, 20 years ago, when I worked on a Redmin project, we offered it in C++ and a little bit Python. Our main challenge was thread safety, because Redmin, it was a remote control software and it was extremely important for it to not crash. But if you offer some system software for Windows, it has literally dozens of threads, and each thread wants to read memory, write memory, open files, close files, and they do that simultaneously. And it was extremely hard. It took me nearly 10 years in order to tackle a little bit of thread safety. So our next topic is how to tackle thread safety in Python, and our speaker from Digital Labs, who is right now putting finishing touches to the Deep Dive Python book. Please welcome Adarsh Divakaran.
Thanks, Grigori, for the great intro. Hey everyone, good afternoon. Today, I'll be talking on the topic of tackling thread safety in Python. So this is about me. I'm Adarsh. I'm a co-founder and lead consultant at Divakaran Labs. At Divakaran Labs, we provide Python and software development consulting to our global clients. So these are the topics for the today's talk. We will start with threading, and then we will look into the issues that happens with threading, which are race conditions, and we will use synchronization primitives to make our programs thread safe. So you might have been knowing threading. Threading is a concurrency framework. So it allows us to spin up multiple threads which can run in parallel, each executing its own piece of code. So why use threading? We use threading to improve application efficiency. So it will help with concurrent execution. It will improve the responsiveness of the application. So let's consider a sample. We have a travel booking application. We have a total of 10 available seats, and we have this symbol book seat function. It just reads the global variable available seats, and if the available seats are greater than 0, we will decrement it by 1, and we will print the message that the seat is booked. Or else, if there are no available seats, we will print that, sorry, no seats are available. Suppose we are using this application in production. There is one issue: bookings get completed sequentially. These are slower. Only one user can execute this script at a time. The other user needs to wait to complete its execution. So the solution is to use as a concurrency framework. In this scenario, let's take the example of using multi-threading. So this is our modified multi-threading booking application. We will be using Python's built-in thread pool executor. We have a thread pool executor here, and we have 10 concurrent threads. So we are using a thread pool executor which will have like 10 available threads, and we have 15 people who are trying to book the seat. We have 10 available seats and we have 15 people, and we are using executor.submit to call the function simultaneously. So we have like 15 threads waiting to book the seat, and the number of threads will be managed by our thread pool executor. We will use executor submit function to run that concurrently. So let's see that in action. This is our sample code. We have like 10 available seats. This is our book seat function. You can see everything is the same. We have a sleep here to simulate a real processing. Maybe in a real application, like we will read data from the database or we will do some network calls. So we have added a sleep here. It adds some delay, which is meant for real processing. Next, we decrement the available seats and prints the messages based on the availability. So as we have seen, we have like 10 concurrent threads. We have our thread pool executor and we are creating 15 threads, and these 15 people will try to get a seat simultaneously. Now let's try to run this script. So you can see that every thread gets executed successfully and our final seat count is -5. Actually, we had only 10 seats, but we oversold our seats. This is because everything depends on reading this available seats value, and there is some delay where we change the available seats. When we decrement the available seats, before we do that, the remaining threads read this value and they enter this section so that everyone gets the seat booked. So the problem is concurrent read and write to shared data. In our case, the number of seats is the shared data, and this leads to something called race conditions. Now, let's take a look at what are race conditions. Race conditions are like unexpected events where our program outcome depends on uncontrollable events, like based on the thread execution order, the output of our program changes. So this happens when we use multi-threading and we have like some shared mutable data. So we have some shared variable which is being operated by our multiple threads. And if an operation is non-atomic, like it happens in multiple steps, they can get context switched in between. Like one thread can stop its execution, pause its execution, and another thread can enter that section. So this is the concept of context switch. So we have a demo for context switching also. This is our code. We have a worker. Worker just loops from 0 to 2. We have a loop in range of 3. It just sleeps for a small bit, and then it prints the name of the current thread and it prints the number of iterations it's doing. It will be from 0 to 2 in our case. Then we have our thread pool executor. We have 4 worker threads. We create 4 worker threads and we submit this task to our threads. Also, you can see I am printing here sys.getSwitchInterval. Let's run this and see what happens. So initially you can see this is the switch interval of my interpreter. This is 0.005 seconds or 5 milliseconds. This means that when I am using threading, my Python interpreter will try to switch between threads in these intervals. So every 5 milliseconds, my Python interpreter is trying to switch between threads. We can see our initially worker 0 is doing its iteration 0, then worker 1 is doing its iteration 0, proceeded by worker 3. We can see each threads are taking turns to complete the tasks submitted to them. If it's a synchronous code, they might execute like one by one. But in our case, one thread executes this line, then it performs a context switch, or interpreter performs a context switch, and the other thread gets access. So each threads are taking turn by turn and executing their own code. So this is what happens in threaded programs. There will be context switches between threads when the code is running in between. Next, let's move to the concept of thread safety. A program is said to be thread safe if there are no unexpected side effects or there are no race conditions. Like our previous booking example, it's not thread safe. There are unexpected side effects for the code. So next question is, when should we worry about thread safety? We have multiple concurrency frameworks in Python. We have threads, coroutines, multiprocessing, and sub-interpreters. So thread safety comes into play when we are using threads as our concurrency framework. Next, along with using threads, our code contains shared mutable data. As we have seen, multiple threads are sharing data in between, and the operations are non-atomic, like operations happen in multiple steps, and this can due to context switches. So there is no problem if no data is shared. These thread safety issues mainly occur because threads share the memory location of the parent process. So due to this, the variable values, everything is shared between these different threads. And if the code is working on immutable data, there won't be issues since there are no changes to data. And if the operations are atomic, like if an operation completes in a single step at the Python level, then that will also be fine, since context switches happens only after a single instruction is processed. So these are our options to make our programs thread safe. First thing is we can go with any other concurrency framework if that specifically better suits our workload. Then we have another option. We can use thread local data. In this case, we can use threading.local function where each thread has its own copy of variables. This won't be shared across threads. Then another option is we can use synchronization primitives. So we will be going deeper into this, various primitives provided by Python. And another thing is we can make our operations atomic. Atomic means one execution or a single instruction gets completed. And if our operation is just one single instruction in a Python bytecode level, there won't be any problem. Something like a single increment operation or something like that. So these are the synchronization primitives present in Python's threading module. We'll be going over each of them one by one. First, we have the basic primitive, it's lock. A lock allows only one thread to access a resource at one time. So we can use a lock to modify critical sections. We can use locks to mark critical sections in our code. So if you are using lock, it ensures that only one thread can modify a shared variable at a time. So this is a classic example. We have seen our booking application. We can exactly use logs to solve this issue. So this is our previous code. We can introduce logs to our book seat function. We have log.acquire. So once a thread reaches this point, one thread can acquire this. One thread can use acquire the log using log.acquire method call. And whenever some other threads reach this point in execution, they get blocked. They should wait for release of this log by the originally acquiring thread. So only one thread can acquire it, and other threads will get blocked at this point in execution, and they will only get access after this is released by the original thread. Similarly, we can use either the acquire and release methods, or we can, for better simplicity, we can use it as a context manager. So this is the usage with the with block or the context manager block in Python. This is similar to acquire and release. So whenever the code enters here, the first line will be like log.acquire. And whenever Python code exits this block, exits this with block, then the release will be automatically called. So now let's take a look into our modified booking application. We had like 10 worker threads and we have 15 workers. Then we are introducing a lock object. It's used to mark the critical section of the code. So we are allowing only one thread to execute it at one time. So this is our code. We have a new lock variable. This is created by creating an instance of threading.log class. This is our log. Then we can see that everything remains the same except that we have our booking code wrapped inside this with statement. So this ensures that only one thread can execute this code, this critical section of the code at one time. Then we have everything else similar. We have 10 worker threads. We have 15 threads trying to perform the booking. Let's see what happens. So now it behaves as expected. We can see the first 10 threads which reached there first could get a successful booking, and for the last 5 threads we can see the message that no seats are available. So this is how we can use logs to make our code thread safe. Next, we have somewhat advanced section of logs. This is our logs. We have previously seen log. It's called a naive log, or it's not that intelligent. So whenever I have a thread 1, it tries to acquire a lock it already holds. Then it gets into a state called deadlock. It blocks the execution indefinitely. So it's just naive. It's not intelligent. So rlock is a re-entrant lock. So if I am currently holding a lock, I can re-enter the code safely. This is useful in nested log scenarios. Let's see an example. It's very similar to the log class. It has like acquire and release methods, and it can be used as a context manager. So in our demo, we have only a one thread. We have a function which acquires a log, and it calls another function. It's like a recursive, not recursive, it have like nested function calls. And the second function also tries to acquire the log. So this is our code. We have a booking log here. We are initially using the symbol log class. Then we have only a single thread. What the thread does is it tries calling this function. This just prints a message. It starts to book a flight. Then it acquires the log. It finishes the booking of the flight, and it calls the book hotel function. Similarly, the book hotel function, it also tries to hold the booking log. Let's see what will happen in this case. We are using a symbol log. So in this case, we can see the message attempting to book hotel is being printed, but our execution is currently stuck here. It's stopped here because the next line is where the log acquisition happens. Here, the thread is trying to acquire a log it already holds. So here is a deadlock scenario. The booking log is already held here. It's not yet released. Inside the code, we are calling this function. So a simple log class cannot handle this scenario. So what we should do is, in this case, we can use rlog. There is nothing much different in the code. Everything remains the same. Instead of log, we are using rlog class. We have only a single thread, and we have the same functions. So in this case, we can see, since we are using rlog, since our thread, we only have one thread, it already holds booking log here. So whenever it's trying to attempt booking hotel, it tries to acquire the same log. Since we are using an rlog, it allows for the scenario, it allows for nested log acquisition, and this completes successfully. Next, we have semaphore. In case of logs and rlogs, we have seen we can use that to mark critical section of the code, and we can allow only one thread to execute the code. But in case of semaphore, it maintains a counter. We can allow a set number of threads to access the resource simultaneously. So we can use semaphore to limit the number of concurrent access. For example, we can maybe use it to limit concurrent connections to a database for connection pooling. Let's see an example. Here we have maximum concurrent bookings as 3, and we are using a semaphore that. We are using a semaphore initialized with the value of 3. This means that only 3 people can book the travel package at the same time. So this is the reason we are using semaphore. We can like limit the number of concurrent operations. We need to restrict. We have 10 workers trying to book a travel package, and we allow only 3 of them to book at a single time. So in the code, you can see that we have total of 10 workers. Then we have a semaphore initialized with a value of 3. We have 10 threads which are started at the same time. We are starting it at the same time without any delays. But we have the with semaphore statement here, similar to log. We are using it as a context manager. And we are using this to execute our booking. So it prints that the travel package has been booked and it's waiting to book the package. And we have added a delay of 1 second for each booking. Let's see what happens when we execute the code. So this is what happens. We can see this is our timestamp. You can see at the timestamp ending with 73, all our threads are in the waiting stage. We have 10 worker threads. Every thread is in the waiting stage. They are ready to perform the operation, but we have our semaphore. So it allows only 3 threads to enter the section. We have workers 0, 1, and 2 here booking the travel package. So at this point, at the timestamp ending with 74, you can see worker 0 has completed the booking, and worker 2 has completed the booking, as well as worker 1. So 3 of the threads has completed the booking. Due to that, at the same timestamp, you can see the next 3 threads are getting the access. So in this way, the semaphore here only allows for 3 threads to access concurrently. Other threads will be blocked as at this point. Other threads will be waiting. Their execution will be blocked at this point, and only when one thread is getting freed after completing this with statement, a newer thread can get access. Next, we have something called event. It's used for signaling. So I can use events to allow one thread to signal that a particular event has happened. It's commonly used for notifying worker threads that new data is available for processing. Let's see an example for that. We have an event called flight landed. We have wait for passengers function and flight status update function. So this is our event object. The status update performs some operations and it sets the event. And the wait for passengers, it has a wait attribute call on this event object. So the code gets blocked at this point until somebody calls this set function. So this is our example. We have 2 threads. One is for updating flight status. We take some delay to update that. And the second thread is waiting to collect passengers. Passengers will be collected only after the flight status has been updated. And both of these threads start at the same time. And they are using event object for communication. So here is our code. We have our event object. Wait for passengers. It initially prints that it's waiting for the flight, and it calls the wait attribute or the wait method on the flight landed object. So the code gets blocked here until the event is set. For the flight status update function, it initially sleeps for a delay of 3 seconds, and then it prints our message and it sets the event. So let's execute that. We have 2 threads, each for executing one of these operations. You can see that the threads start at this timestamp ending with 77. We have a sleep time of 3 seconds. So whenever this 3-second delay completes, we are setting the event. Only then our passenger thread can proceed to printing its message that it's collecting the passengers. So this is used to signal the occurrence of events. Multiple threads can signal other threads that something has happened, and other threads can wait indefinitely until the event has been originally set. Next, we have something called barrier. So barrier coordinates multiple threads. They allow multiple threads to wait until a certain point so that all threads have reached a certain point in their execution so that they can proceed together. It's like, let's think of an example. This is where we can ensure that all worker threads complete their individual tasks before any thread proceeds to the next phase. Suppose we have like multiple stages of transactions, we can ensure that every thread has completed the first stage before it proceeds to the next. So we have barrier.wait. Initially, we can create a barrier object by providing it the number of threads it has to reach the barrier. Currently, we have 4 travelers and we are initializing this with 5. So this means that we can add the barrier.wait somewhere in our code. So whenever a thread reaches this statement, it increases the thread count by 1. Here we need 5 threads to reach this wait statement so that our code can proceed further. Let's take an example. Consider the case when there are 4 travelers and a tour guide. So we have like total 5 people, and guide is ready at the start and travelers take a random delay to get ready. So we can use a barrier to synchronize this. This is our code. We are using a barrier and initializing it with a value of 5 since we have 4 travelers and 1 tour guide. This is the traveler function which models the behavior of a traveler. It initially prints that the traveler is getting ready. It waits for a delay to simulate the traveler getting ready, and once the traveler is ready and waiting, we have a barrier.wait. So all the threads will get waited here. All the threads will get blocked here unless total of 5 threads reach the wait statement. Similarly, for the tour guide also we have the same thing. The tour guide is ready from the start. There are no delays. The guide is initially waiting. So we have like wait conditions in 2 sections of our code. So collectively, there should be 5 threads hitting at the wait condition so that our code can proceed to the next statement. We have like 4 threads and we are creating 4 for travelers and 1 for guide. Let's see what happens when we run that. So you can see everyone starts to get ready at the same point. Tour guide is already, since there is no delay, tour guide is ready from the start itself. So each travelers are getting ready one by one. So at this point, you can see see that traveler 1 is ready and waiting. Traveler 0 is ready and waiting. Now 2 is ready and waiting. At this point, we have 3 of our travelers ready, and we also have our tour guide ready. Next, we only have our traveler 3 remaining. Here at this point, at this timestamp, traveler 3 is also now ready. That means all our threads, like total 5 threads, have reached the wait condition. And at this point, at this timestamp, we can see everyone is starting the tour. So the case here is that we are waiting for total 5 members to reach this barrier.wait statement. In our case, we have our tour guide has hit the wait condition from the start. That increments the value to 1. And we have 4 travelers. So after all the travelers is ready after the delay, after the 4 travelers hits the barrier.wait statement, we can see everyone is ready and the tour gets started. So this is used for coordinating between multiple threads. We can block all the threads before they proceed to the next stage in a transaction or operation. Next, we have condition, which is our final synchronization primitive. It's a bit of complex one. It allows us to wait for certain conditions to be met. Also, it is associated with a lock. So we have scene lock. we have used lock for like exclusive access. We can use locks for marking critical section of the code. And we can use, along with that, we can use a condition to ensure that certain conditions are met before our threads can proceed. So a practical use case is posting a thread until specific condition is met, such as waiting for a queue to be non-empty. So this is commonly used in producer-consumer scenarios. We have a producer creating something or adding some value, and there is some consumer which is processing on these values produced by the producer. So this is an example of the condition. We are creating a condition object. Then when using the with statement, this will act like a lock, and we can use the notify method on that. Similarly, for the this is the case for producers. Now we have consumers. Consumers, similarly, we are using a lock using the with context manager. Then we have the wait statement. So we have seen there is a notify function and there is a wait function. So the wait method releases the lock. It blocks until another thread awakens it by calling notify. So wait is for waiting something, waiting some event. The code blocks at the wait stage, and the notify function, it's used for notifying of the condition. Like whenever a new thing is added to the queue, we can call the notify function, and it will awake one thread which is currently waiting. Or we can use notify all. It awakes all the current threads which are waiting at this point. So let's take a demo. We have one travel agent and 5 customers. The travel agent serves one customer at a time. Then we have a customer queue which stores active customers. Queues shared across threads. Since this is a list, this is shared across threads. So we are using a lock to access this to prevent, like we have seen, the global mutation. To protect that from across threads, from modified across threads, we are using a lock here. And we have a customers list which stores the customer name and the delay of their arrival. So this is how the customer gets served. When the travel agent is free, he or she will immediately serve the customer arriving. If the travel agent is busy, the customer should wait until the current customer is served. So this is the code for our condition. Here we have 6 workers. We have our 5 customers. First customer arrives after a delay of 1 second. Second customer arrives after another delay of 1 second. We have 6 threads, one for our travel agent, and for each customer we will create a thread after the delay specified along with their names in this customers list. Then we have add customers to the queue. This is the producer of our application. Whenever a new customer arrives, we are holding the lock since we are operating on like this globally shared list. This list is used to denote the customers waiting to be served. So along we hold the lock. This is our condition object. You can use it as a with context manager, and this will act as a lock here. So inside this, we are adding this to customer queue, and we are using a notify. So notify wakes up one of the waiting threads. This is our serve customers thread. This is what runs representing the travel agent. We have an infinite loop, like it should work on serving customers unless stopped. So it initially holds the lock since we are working on shared data, shared queue. Then here is the wait statement. If the customer queue is empty, it calls the wait statement so that it blocks indefinitely. It waits for the arrival of one customer. Here you can see we have acquired a lock, but the thing with condition is that whenever a wait is called, it automatically acquires the lock. So in this way, another operation, like maybe the add customer to queue can run using the same lock. Since we are waiting, at waiting time, the condition releases the lock. Then once we get a customer, the customer is popped from the customer queue. Then we will serve the customer. We will take 1 second to serve the customer, and we will print the message that the customer is done served. So you can see that at the initial time, the travel agent is ready, but at the timestamp ending with 29, there are no customers. So the travel agent is waiting. At the timestamp ending with 30, customer 1 has arrived. So immediately the travel agent starts serving them. Then at 31, customer 2 arrives. Once the travel agent has served customer 1, the travel agent is free and they start to immediately serve the customer. Next, we can see that whenever the travel agent is serving customer 3, 4 and 5 has arrived, but they have to wait until our travel agent is free. You can see that the customer 4 can enter only after the service of customer 3 is finished. So this way, we can use condition to manage shared resources, and we can notify waiting threads that certain condition has occurred. In our case, it's the arrival of customers. So condition is a bit different from other primitives. It involves a lock. It can act as a lock when used as a context manager, or we can call the acquire and release method, and it has some additional methods. These additional methods are wait and notify. So the lock will be used when we use condition object as a context manager. Whenever the wait is called, this is the thing that is special with the condition object. Wait method is called, it releases the lock. So the other threads can access the critical section, or they can proceed with their own actions. Next, we have seen that we have used event. We have used the flight landed event to manage some events. One thread can notify the other that certain thing has occurred. But let's take a look at the difference between condition and event. Events are commonly used to handle one-time simple one-time events, but conditions are used for producer-consumer scenarios where there is a continuous flow of events happening. So we have our travel agent waiting to serve the customers in an infinite loop. So there is a infinite flow, like customers can come at any time. There are a number of events flowing, and condition allow us to handle events. Plus they can we can use them to get exclusive access using locks. So we can use it as a lock also. Specifically, we use conditions when we need to handle events, and we need to manage something called a lock, or we need to have some exclusive access to sections of our code. So that's it. This is summary. So suppose we have we have a simple code, and we are trying to increase our speed or responsiveness by introducing multi-thread. Should keep in mind that the code we are working with might not be designed for thread safety in mind. For example, even you can see that some of the sections, some of the codes maybe in the standard library might not be thread safe. In our case, you can see that I'm using a print here. The new line is by default, the print statement prints something, and it prints a new line after that. The next statement happens at the next print happens in a new line, but you can see the print statements are producing interleaved outputs here. So this is a thread safety issue found in Python in Windows. So some of the library functions may not behave as we expect when we are running multi-threaded code. Then we should check for shared mutable data and atomicity requirements of our code. Then finally, we should add synchronization primitives. We should add proper synchronization primitive to enforce thread safety in our code. So as the CPython documentations advise, when in doubt, we should use a mutex to allow mutual exclusion and thread safety in our code. That's it. Thanks, everyone. You can get the talk materials and connect with me at the following link, linkhq.co/Adarsh. Thank you.
Please use the QR codes to rate the talk. And now we have 4 minutes and 30 seconds for our questions. And will you be able to name the best questions so we will give them our little prize? Is it okay with you?
Yeah.
Okay, you need to remember which one is the best. And the first question from our hall, you can ask in English or you can ask in Russian, and I will translate, whichever is more comfortable to you.
Thanks for your presentation. And my question is, you have shown in your first code example that we can get a switch interval value. So is it possible to change its value, and when I should consider doing it?
Yeah, similarly, we have a set switch interval value. We have seen set get switch interval. It's to get the value. Similarly, we have the sys module has the set switch interval, so we can use that. I don't think in normal cases we should change that. Maybe it's maybe possible to do that if we are doing some extension modules like we are using the C Python level. If you are working on like C level extension modules or something, in our normal cases, that won't need to be changed. If you are working with something and you are sure that, you have to tell the interpreter that just check for context switching every 1 second. You can set that to 1. But I think in normal cases, we do not know how long our threads take to execute. So this is like after executing one statement, the interpreter should ideally, after executing one single statement, the interpreter should check that. So this is ideally the time which we will take for executing our one line of code, but we cannot know that beforehand. We are mainly using threading for something like network calls or IO operations, something like that, where we do not have like much control. So yeah, I think in normal cases, we do not have any utility for changing that, but we can do that.
Okay, thank you.
Next question, please.
Yeah, thank you for presentation. At the last slide, you said that if you're not sure, please use thread safety primitives to enforce thread safety. But I think it's very heavy-weighted operations. Maybe you can advise some tools, some libraries to check your code and find some places in your code where thread safety may be the issue.
Yeah, so the recommendation I have shared is from CPython documentation. So one thing is, I'm not aware of some tools or something. The thing I suggest is that, suppose we have some operations, maybe we are introducing multi-threading and each thread executes on, if we have like, that is our keywords, if we have like shared data, globally shared data, here we have, we had like our number of available seats that's being shared across threads. If some data is shared across threads, that should be checked. Then the cases with non-atomic operations, we had non-atomic operations like we read some variable value at one point, we do some printing and all, and we modify the value at some other point. So if there are operations that are happening in multiple stages, these are non-atomic operations, they are like multi-stepped operations, then we should use a synchronization primitive in that case also. So then when there is like shared mutable data should be shared across threads, that should be mutable by different threads, and the operations are like multi-stepped, and that way they are non-atomic. So these are the two cases we should check.
Next question, please.
Hi, thank you for the talk. I have a question. You've mentioned the recursive locks that are allowed to be taken by the same thread if we use them in the recursive functions. Are there something like that for semaphores, barriers, or events, for example? Especially for semaphores.
No, for semaphore, I think semaphore is for that particular purpose. Like we have Suppose we have only 5 resources. We only have 5 concurrent connections to a database. So in that case, we should use a semaphore. That means it can be hit by any number of threads, but only 5 threads can access that concurrently. After 5, it will get stopped. So if we hit again with the same thread, it's executing something, right? So that will increase the number. It has a counter associated. So there is no way like we can handle that specifically. Whenever the code is being hit at once, it will raise the counter by 1. There is no recursive checks available.
Okay, thank you.
Yeah, semaphore is much more like a counter, so making it recursive is a little bit tricky. I think our time is up. Please applause to our speaker.